Welcome back to elementary statistics. In this video, we're going to be calculating standard deviations. The standard deviation is one of the most important measures in statistics. We're going to be building on it throughout the course. But the formula and the process for calculating standard deviation is intimidating if you're not used to it. So before we get into any of those details, I want to spend some time and just look at how the formula works, how to use it, and how to keep in your mind how to approach problems using the standard deviation. Right. So before I get into that, just a little bit of what the standard deviation is doing and what it means. The standard deviation builds off of a statistic called the deviation from the mean. Deviation from the mean is calculated by taking an individual data point and subtracting the mean from it. And the deviation from the mean can be used in a very straightforward manner because it shifts the distribution so that the distribution has a mean of 0 instead of any other value, which is interesting in its own right. It allows us to do a lot of comparisons between different distributions relatively easily. And it also allows us to do a number of comparisons within a distribution relatively easily. But it leads to a natural question. What is the deviation from the mean on average? Now, the mean of the deviation from the mean is right behind my head going to be 0 every time. So we need a different idea of average. I mentioned when we were talking about central tendency that there was an idea of average called the root mean square, which was very helpful when you're dealing with a distribution that has both positive and negative values like this one does. And so that's going to be the idea. The standard deviation we're going to take the symbol for it is this guy. This is a lowercase sigma. It kind of looks like the letter O with a really long tail on it, right? If you are writing in cursive, the letter O kind of looks like that. It's the same idea, but we cut off the early part and we make the tail kind of a little bit squiggly. And that gives us the Greek letter sigma. All right. So to calculate sigma, we are going to take our deviations from the mean, x minus mu. We're going to square them so that they are all positive. And then we're going to add together all of those squares. Divide by the number of scores in the distribution, and then undo the fact that we squared earlier by taking the square root. You will also see, and we'll come across some calculations later on, where the variance is also of importance. The variance is literally the square of the standard deviation. So do the same process. except don't take a square root. Again, later on, much later on in the course, we're going to look at several places where the variance is useful. But in the immediate future, the standard deviation is going to be the more useful tool for us. So when you're thinking about variance, I want you to think about that as a calculation check. When you're working with the standard deviation, you are going to take a square root. And taking a square root has the effect of compressing larger numbers, numbers that are far apart before you take a square root. After you take the square root, are relatively closer together if the number is bigger than, say, 2. And most of the numbers we're going to be looking at are going to be 20, 50, 70, not 1, 2, or half. And so the variance is useful as an easy way to check and see if you are making a conceptual error or a rounding error. If your variance is very close to the correct variance, but your standard deviation is off, that means that something went wrong in how you rounded. If your variance is off of the correct value, that means that something went wrong earlier in your calculations. All right, so if we want to calculate a standard deviation, the first thing we need is a population. Notice here that I've been using the letter mu for the mean. The letter mu is used in a population. So when I'm looking at the values I'm going to include, I need to have an entire population to work with. So let's look at a very simple set of data. There are 6 scores in this distribution: 1, 2, 3, 4, 5, and 6. These are the possible results that you can get when you roll a single 6-sided die. Not a very interesting population, but it is a population. It is every possible score for rolling one 6-sided die. Right, so the first thing I need to do in order to calculate a standard deviation is to calculate the mean. I notice that there are 6 scores in the distribution. If I add all of those scores together, 1 plus 2 is 3, 3 and 3 is 6, 6 and 4 is 10, 15, 21. And then the mean is 21 divided by 6, which comes out as 3.5. Now I'm going to go back to my list of values and I'm going to start moving across the page. I'm going to introduce a second column where I'm going to calculate the deviation from the mean for each score in the distribution. So I take 1 minus 3.5, which comes out at negative 2.5. I take 2 minus 3.5. I take 3 minus 3.5, 4 minus 3.5, 5 minus 3.5, and 6 minus 3.5. And that gives me the deviation from the mean for each score in the distribution. Now my formula for standard deviation, which is just off screen here, says I don't just want the deviation from the mean, I want to square all of those things. So that's a new column. I'm going to take my x minus mu and I'm going to square it. So negative 2.5, the whole thing squared. Now here is where the biggest mistake happens. The most common mistake in calculating standard deviations is right here. I have a negative number and I'm squaring it. You should remember from algebra that whether a number is positive or negative to begin with, if you multiply it times itself, positive times positive is positive, negative times negative is positive. And yet, if I jump over to my calculator and I try to put in negative 2.5 squared, my calculator tells me the result is negative 6.25. And the reason is that calculators are making a mistake compared to humans in the order of operations. It is a flaw in how calculators are programmed, and nearly every calculator is programmed this way. And so we have, as a collective, mathematics educators, decided that we should bow to technology and just teach things the way calculators teach them. And specifically to get around that, we need to put parentheses around the negative 2.5 before we square it, and then we get the positive value out. Or you can take the lazy approach, and you know that whether the number is positive or negative to begin with, the result is going to come out positive, and just leave the negative off when you punch it into your calculator. All of those approaches will work. I think this is the fastest one, and it allows us to quickly get through all of these calculations. So negative 2.5, the whole thing squared, is 6.25. Negative 1.5, the whole thing squared, is 2.25. Then we have 0.25, and actually the same numbers repeating. When you have positive 0.5 squared, you still get 0.25. Positive 1.5 squared is still 2.25, and positive 2.5 squared is still 6.25. Once you get the hang of this process, you'll start leaving the actual calculation off, right? We have our x values. We know we need x minus mu, and we can do 1 minus 3.5 equals negative 2.5 without actually writing down 1 minus 3.5. Likewise, we can do negative 2.5 squared and get 6.25 without literally writing down negative 2.5 squared. Right? Saving yourself writing like that is absolutely valid and absolutely valuable when these get a little bit messier. But for right now, going through and doing the calculation step by step is a good way of learning and internalizing and making sure you understand how to use this formula. Right? But now that I have all of these, again, if I scroll back up to the formula, I want to take all of my x minus mu squares, and I have a summation symbol. So I want to add all of these things together. That's what comes next. So the sum of all of these, I add 6.25 plus 2.25, which is 8.5, plus 0.25, plus 0.25, plus 2.25, plus 6.25, and I get 17.5. Then from here, the variance, sigma squared, is 17.5 divided by 6. My calculator is happy to tell me that 17.5 divided by 6 is something on the ballpark of 2.92. And then my standard deviation is the square root of that number. And the square root, come on, the square root of that number comes out somewhere in the ballpark of 1.71, or somewhere thereabouts. All right, so this process is the standard deviation of a population. If you know all of the scores for the entire population, all of the data values that you could possibly have, you can calculate the standard deviation of a population. As we've established, having a population and having data on the entire population is rare. So actually, the most important thing to take away from this calculation is the symbol, which I'm standing in front of. Sigma squared is the variance of the population. Sigma is the standard deviation of the population. We are typically going to talk, instead of populations, about samples. And when we're dealing with samples, it turns out that sampling has a tendency of underrepresenting outliers, which makes sense. If there's a very small number of outliers and you are collecting a small sample to be representative, the representative percentage of an outlier might be less than one whole person. And so if the standard deviation and the variance and the deviation from the mean are trying to interpret how far data points are from the mean on average, a sample will underrepresent that value. And so there's a simple fix that has been introduced. Sorry about that. All right, if we want the standard deviation and the variance of a sample, well, instead of calling it sigma, we're just going to call it S to give a distinction, sample versus population. And the variance, S squared, looks almost identical. We're going to add up all of the x minus, remember the mean of a sample is x bar, not mu. But we'll take all of the x minus x bars, we'll square them, we'll add them all together, and then we'll divide. Instead of by n, we're going to divide by n minus 1. And again, the reason that we want to do this is that when we have a sample, we are underrepresenting outliers. And so we want to try to come up with a way to make the standard deviation a little bit larger. And subtracting 1 here, if you have a small sample, right, the difference between dividing by 10 or dividing by 9 is pretty significant. The difference between dividing by 5 and dividing by 4 is very significant. The difference between dividing by 100 and dividing by 99 is less significant. The difference between dividing by 1,000 and dividing by 999 is almost negligible. So if you have a large enough sample, this difference is not going to be noticed. If you have a small sample, this difference is going to help us make the standard deviation a little bit larger to account for outliers that were underrepresented in the sample. Right. So we have the variance, and then of course the standard deviation is just the square root of that same thing. And the calculation looks very much the same. If I have a set of scores here, we'll call X. Let's go with a very small sample distribution this time. We have scores of 21, 25, 27, and 28, if I can actually write. Right. And we can go through the same process. We can find the number of scores in the distribution. In this case, there are 4 of them. We can add all of the scores together. My calculator is happy to tell me that this comes out at 101, and then we can divide. X bar is 101 divided by 4. Which is 25.25, but I'm going to round to 25.3 just to make my life a little bit easier. All right, a general rule of thumb, round calculated values 1 digit further than the actual data in your distribution gives you a good enough approximation. But from here, we continue the process the same way we did in the previous example. We'll take x minus x bar. 21 minus 25.3 is negative 4.3. 25 minus 25.3 is negative 0.3. 27 minus 25.3 is 1.7. And 28 minus 25.3 is 2.7. Then take each of these numbers and square them. 4.3 squared is 18.5. 0.3 squared is 0.09. I'm going to round that and call it 0.1. 1.7 squared is 2.89. I'm going to round that and call it 2.9. And then 7.3. Then from here, we want to add together all of the x minus x bar squareds. So 18.5 plus 0.1 plus 2.9 plus 7.3, my calculator tells me comes out at 28.8. And then I take that number, I divide by n minus 1. 4 minus 1 is 3. 28.8 divided by 3 is 9.6. And then finally, the standard deviation is the square root of that number. And my calculator is very happy to tell me that the square root of 9.6 is somewhere in the ballpark of 3.1. All right. So those two formulas are the usual form of the standard deviation formula. That very slight change between the standard deviation of a population and the standard deviation of a sample is pretty easy to remember. I think that it becomes very apparent very quickly that the bigger your distribution is, the more time-consuming this process is going to be. Because you have to go through, you have to calculate the mean, which is a place where rounding errors can occur. You have to calculate the deviation from the mean of every single point. You have to square all of those. Rounded values squared are even worse rounded, and then add all of that together. And so it turns out that it's possible to substitute in the definition of the mean, right? The mean is the sum of everything divided by the number of things. If you take that and plug it back in for the mean, in the formula for the sample, unfortunately, this doesn't work for the population. It relies on the fact that we have an n minus 1 down here. But if you plug that back in here, and you expand things out and you work through everything carefully, it turns out that you can rewrite this formula in a way that's a little bit more efficient. For the small sample that we're looking at here, it's not going to make that much of a difference. But we can calculate the variance s squared by multiplying n times the sum of x squareds, then subtracting the sum of x's squared, and dividing by both n times n minus 1. Right? I think that formula makes a little bit less sense than the one we just finished working with. So let's go back. Let's look at the exact same distribution. All right. We had x values of 21, 25, 27, and 28. The reason that the shortcut formula is useful is that the only other column you need here is an x squared column. I want to square each of the scores in this distribution. So 21 squared is 441. 25 squared is 625. 27 squared is 729. And 28 squared is 784. I want to notice that there are 4 scores in this distribution. I want to add together all of the x squareds. So that's 441 plus 625 plus 729 plus 784, which my calculator tells me is 2,579. I also want to add together all of the x values. 21 plus 25 plus 27 plus 28. We did that in the previous problem. That comes out at 101. But then in the formula here, when I have my sum of all the x values, notice the square outside the parentheses. That means add up all the x values, and then when you're done with that, square the whole thing. So if I take 101 and I square it, I get 10,201. All right. This is an ugly formula, but it absolutely works. And as you'll see in the next example, it can really save you a lot of time and headache. All right, so let's see. We've got n, which is 4, times sigma x squared, which is 2,579, minus sigma x, the whole thing squared, which was 10,201, divided by n, which is 4, times n minus 1, which is 3. Right? If you are comfortable using your calculator, you can punch this whole thing into the calculator in one go. In order to avoid mistakes, I'm going to do this in 2 steps. In the numerator, 4 times 2,579 minus 10,201 comes out at 115. In the denominator, 4 times 3 is 12. And if I divide 115 divided by 12, I get, well, 9.58, etc., but that rounds to 9.6, which is exactly the same variance that I got in the last one. And when I take the square root, I will get the exact same standard deviation that I got when I went through this the first time. When you are dealing with a short distribution like this one, I find that the shortcut variance and standard deviation formula actually takes longer than the original one. The numbers certainly are a lot less pleasant, and that's something we can always try to worry about. But the shortcut standard deviation is going to really shine if we have to work with a grouped frequency distribution. So consider this frequency distribution where we have 7 classes, each one has a relatively low frequency, but it's something we can work with. We've seen in the past that when we have a grouped frequency distribution, instead of thinking about the class as a range of data, it is a nice approximation to find the midpoint of each. So we take 5.5 plus 10.5 and divide by 2, and we get 8. We take 10.5 plus 15.5, we divide by 2, we get 13. Let's put that in the right place. 18, 23, 28, 33, and 38 as the midpoint of each of these classes. We could, from here, go through the same process that we used previously. If I want to find the standard deviation, oh, there we go. If I want to find the standard deviation of this distribution, I can use the original formula. I can find the mean. I can subtract the mean from each of these, add up all of the squares, and then continue from there. But since it's a grouped frequency distribution, that means that I have to worry about subtotals on all of these steps. And that gets to be pretty messy. I'm still going to have to worry about subtotals if I use the shortcut method, but at least I have to go through the table a fewer number of times, and that'll make life a little bit easier on me. So that's why that's the approach that I'm going to take here. I know that I need all of my XMs, all of my midpoints for each of the classes. I know that for the shortcut formula, I also need to take each of those and square them. So I get 8 squared, which is 64. I get 13 squared, which is 169. 18 squared is 324. 23 squared is 529. 28 squared is 784. 33 squared is 1089. And 38 squared is 1444. Then I need to add these columns together. Well, there's only one 8, that's boring, but for some of these other ones, like the 23, shows up 5 times in the distribution. So I could remember that and add 23 to itself 5 times, or I could create a shortcut column by multiplying the frequency times xm, and then the frequency times xm squared. All right, 1 times 8, 1 times 64, again, very simple. 2 times 13 is 26. 2 times 169 is 338. 3 times 18 is 54. 3 times 324 is 972. 5 times 23 is 115. 5 times 529 is 2,645. 112, 3,136, 99, 3,267, 76, and 2,888. All right. There are the tools that I need. Now it's just a matter of starting to combine things. All right, the number of scores in the distribution is the sum of all of the frequencies. 1 plus 2 plus 3 plus 5 plus 4 plus 3 plus 2 should come out at 20. We're also going to need the sum of all of the xm's, which again, we're going to use the subtotal where we multiplied by the frequency here, 8, 26, 54, 115, 112, 99, and 76. Add those all together, you get 490. And the sum of all of the xm squareds comes out at 13,310. All right. My favorite part of this whole process, now that we've gotten that far into it, we actually don't need any of the table anymore. I can get the whole table out of the way, and all I need is those 3 summary numbers. I need those 3 summary numbers, and I need the shortcut formula. S squared is n times sigma x squared minus sigma x, the whole thing squared, all over n times n minus 1. N is still 20. Sigma x squared came out at 13,310. Sigma x came out at 490. We want to square that. We want to divide by 20 times n minus 1, which is 19. Right. Once again, if you're very comfortable using your calculator, you can evaluate this whole thing in one go. But I find that it saves me from making mistakes if I at least break it down and do the numerator. In one go, 26,100. And then the denominator, 20 times 19, comes out at 380. And then do the division in a separate step. So I get here something rounds to about 76.6 as my variance. Then that's why things won't look wrong, because I typed that in wrong. That should have been 26,100. And then I get 68.7. That's the number that I had sitting around. That makes me a lot happier. All right. And then last step, once we have the variance, the standard deviation is the square root of that, and the square root of 68.7 is something on the ballpark of 8.3. All right. So barring errors in your calculator, now is probably a great time for me to mention that when you're performing calculations on a calculator, I encourage you to always do the calculation twice. Punch the numbers into your calculator, write down what you got, and then punch it back into your calculator and make sure you have the same thing that you had written down. It's an easy way to check for stupid little mistakes like the one that I just made. In any event, that's all I have to talk about on doing the calculation of standard deviation. In the next video, I'll talk a little bit more about what it means and how to interpret it. I'll see you then.